Let's take a look at electric potential on worksheet 33-2. Okay? Number 1 reads as following. Just as PE, potential energy, transfers to KE for a mass lifted against gravity, shown on the left, okay, the electric potential energy of an electric charge transforms to other forms of energy when it changes location in an electric field. When released, how does the KE acquired by each compare to the decrease in PE? A lot of scientific terms there, right? Okay? Here's what's going on. Remember, we use one analogy to understand electrical fields. We look at gravitational fields, right? Because that's something that you encounter more in real life, like in sports and things like that. Okay? So, how many of you guys lift weights? Anybody lift weights in here? Okay? If you go to like the weight room, it looks stupid because people are just picking up heavy things up and down, up and down. Like, what's with that, right? What are they doing, right? But it's not stupid. The point of weightlifting isn't just to pick something up, but you're training your muscles. However, you only get a workout because you're lifting against who? Against gravity. It takes energy to lift a mass against a gravitational field. And because of that, you can store energy in a gravitational field. So when you lift a weight up, okay, you have to do work on an object and you store it up against gravity. That's called potential energy. And maybe a way to think about this is like in elevators. Okay, a lot of times in elevator systems, when an elevator comes down, it's actually connected to a big lead weight. Okay, because as the elevator comes down, it loses its potential energy and it can do work on lifting that lead weight up against gravity. Say this is like a lead weight. Okay? And that lead weight now has energy stored in it against gravity. So now when you want the elevator to come back up, just let the lead weight do what? Let it fall, and it can help to lift that elevator up. Okay? So when something falls, the energy of motion is called kinetic energy. That energy is not lost. It's just transformed. Maybe another way to look at that, too, is like a roller coaster. Literally, a roller coaster is just a box on wheels. It coasts. There is no motor or engine inside a roller coaster. And so the first thing you ever notice when you get in a normal roller coaster is you go up a really big what? A big hill. It goes because it's lifting up and it's storing up potential energy in that coaster because there's a motor not in the coaster, okay, but by the track that pulls a chain that can drag that coaster up. And so literally what you're paying for when you get on a roller coaster is not gravity. Gravity is free. It comes with your subscription to Earth as Earthlings. Welcome, we come in peace, okay? But you're paying for a way to fall along a track through corkscrews, loops, boomerang turns, etc., and not die. But also you got to pay for the energy to get you up there and all the marketing and Bugs Bunny and Twicket and Dippin' Dots and all that good stuff, okay? Now, for electricity, let's look at electricity here, okay? Here we have a negative source. So what would happen to a positive test charge? It would be what? It would be attracted. So what kind of electric field does a negative point source look like? An attractive field or a repulsive field? Attractive field, like a computer lab, right? So if we release this charge here, it's going to fall and pick up kinetic energy. So the question asks, how does the kinetic energy acquired, the energy of movement of that charge compared to the potential energy? Well, it's just going to be the same because the energy that you put in is the energy that you get out. You don't get something for nothing. So in other words, when you're listening to your stereo, you're running your flashlight, the energy's got to come from somewhere in order to go somewhere. And what you put in is what you're going to get out. Okay? And gravity is a good way to look at that. Another analogy is given in number 2, where we have a spring. It says a force compresses the spring, and as you put a force on the spring, work is done, which is equal to the product of the force times distance put on that spring. Work equals force times distance. And the work done goes to storing up potential energy in that spring. So a way to look at a positive source is to think of it as a spring, where on a positive test charge, we now, instead of an attractive field, we have a repulsive field. Okay? That's pushing away this test charge. So as we push on this test charge closer to that charged sphere, the work done is going to be equal to the average force multiplied by the distance to move that charge. Work equals force times distance. This work is going to be equal to the potential energy given to that test charge. Now if this test charge is released, just like squishing the spring and letting it pop back out, it'll fly past its starting point, and its gain in kinetic energy is going to again be equal to its decrease in potential energy. In other words, in order to understand electric potential, we're going to use analogies like gravity, like squishing a spring. like going up a ski hill, okay, like lifting an elevator, just because it's very abstract. But if you think of voltage as an electric pump to create pressure, to lift charges through an electric field, okay, it makes it a little bit less weird. Okay? Now, let's see if we can complete these little statements at the bottom. It goes as follows. At any point, a greater quantity of test charge means a greater amount of potential energy, but not a greater amount of potential energy per quantity of charge. This quantity, potential energy measured in joules, and potential energy per charge measured in volts are different concepts. They're related but different. One is energy per charge. So, electric potential energy per charge we call electric potential. Okay? That's a scientific term for it. It's commonly measured in volts, so we commonly simply call it voltage, and that's what you're used to in everyday language. But technically, voltage is not the scientific definition of electric potential. Okay? Electric potential is a proper term to define potential energy per charge. If you could take a look on the other side now, okay? We're going to put some math to this, and now you're going to see that it's actually not too bad, which is why I want to go over this with you guys, okay? When a charge of 1 coulomb has an electric potential of 1 joules, it has an electric potential of 1 volt. How about if you have 2 coulombs of charge to potential energy of 2 joules? Well, voltage is equal to energy divided by charge, okay? So if we have, what? 2 joules of energy divided by 2 coulombs, this is still going to be what? 2 over 2, it's still 1 volt. Okay? So in other words, the reason why we have different sized batteries is for convenience. Okay? These guys are all 1.5 volts. They still give you the same electric potential, but these are necessary for big electrical devices like flashlights and stereos. These are for convenience, so it's not too heavy like your calculator, etc. Okay? For homework tonight,